Hi there, welcome to this 6th video in the yt-napari tutorial series. We're going to be covering some time series analysis using yt-napari. Specifically, we'll talk about how to load in samples from time series via the GUI in Napari. We'll go over how to specify the data files you want, how to load in slices through all those data files as individual image layers versus a single image stack. We'll talk about loading in samples from regions through time, talk about what you have to think about in terms of memory usage, and then we'll cover how to do all of those same things from a Jupyter notebook. So we'll talk about the yt-napari time series module and how to use that from a Jupyter notebook, and then cover the same spatial selections as in the GUI. Next video we will actually continue the time series theme a little bit and talk about how to load in regions using Dask in a lazy way so that you don't overwhelm your memory, but you can still interact with your 3D sample through time. Today we'll be using the EnsoTiny cosmology dataset from ytproject.org/data. We'll use all the time steps, so even if you've already downloaded the sample EnsoTiny cosmology dataset with yt.loadSample, you'll still want to go fetch the full dataset here. And thanks again to CZI. Okay, so here we are. I've got my yt-napari tutorials environment activated already, and we're going to start by looking at the graphical interface for the time series loading. So in the plugins yt-napari, we have this yt time series reader, and it behaves much the same way as loading in samples from single data sets, where you specify information on what files to actually load in as your data, and then the buttons down here for adding region and slice selections behave exactly the same way as a single data set. So let's get rid of that region I just added. So the fields up here, not all of them are required, but is the directory field here. This string will be treated as a directory prefix for anything else you enter in the other entries here. And the file pattern here behaves exactly the same way as when you're using the full yt time series object. So you can match, use wildcards to match file patterns and pick up all of the time steps. So for example, this let me put up a new terminal. Let's go take a quick look at what our tiny cosmology dataset actually looks like. So tiny cosmology. So in here we have a bunch of subfolders. The dd with the 4 integers corresponds to all the time steps we have. So we have from 0 to 45 or 46, so 47 total time steps. And so if we wanted to pick up all of these, you would just specify dd and the 4 question marks to select any of the integers there. So let's start with a slice. So let's get a gas density slice, normal to x. Let's put it in the center of the domain and slice through the whole domain. So if we just hit load selections like this, it would go through every one of these files that corresponding to each time step, apply this slice and return a separate image layer. And so if we don't want all of those initially, there's a couple ways to limit it. So one, you could just explicitly list which files you want. So let's do that first and then come back to the wildcard. So let's say we wanted the 10th and the 20th time step here. And just hit load. it'll go in and sample just those 2 time steps and load them in as separate layers. So you can toggle between them. Remember that when you're loading in separate layers initially, they won't be linked together, so they won't be normalized. So if you link them, select the 2, right-click, link, then after you adjust the settings up here, it'll get applied to both layers so that you can normalize between the layers easily. And then let's unlink these, and now when you toggle, these are on the same color map. So let's get rid of those. Right, so the other way to limit your selection is if you supply a file pattern. This file range here will build a Python range object. So this is the start, the end, and the step. And so it'll use that range object to subselect from the list of files that get matched. So let's say we want to go from the second time step to the final time step, sampling every 5. You hit load, and it would go and load every 5th time step between there as a separate image layer. This time though, we're going to hit this load as stack button, and what that does is instead of loading separate layers, it takes the slices from each time step and creates a single 3-dimensional image stack where one of the axes is the time axis. So let's move that out of the way. So now we're in a 2D view, and as you move the slider down here, you actually go through time. And you can hit the play button to animate it. One of the fun consequences of loading in as 3D or slices is that if you switch to a 3D view, you can actually look at your slices in 3D. And since we only have 5 slices, that's not super interesting. So let's actually get all of the slices. So because we're using slices here, there's no worry about fitting all these slices in memory generally, unless you change the sampling resolution to a much higher value. Cast density, load them all, load them as a stack. Okay. Oh, forgot the axis. And as this goes, you'll notice the little busy signal down below on the bottom right here, just telling you that something's going on in the background. This is all happening in a separate thread, so it doesn't lock the Napari window, but it is all happening in serial, so you do have to wait for YT to load up each data set sequentially. Okay, switch back to 2D. So now we have from 0 to 46 index, so we have the full evolution that we have available to us now. And now when we look in 3D, we get a little bit more, actually let's switch the color scale here. You can see a little bit more of that time history in that 3rd dimension. I'll show you from the notebook. You can actually control how this time axis scales so that you can really blow this up if you want to look at the history in 3D, in this 3D view. But from the GUI, you can't do that. So let's delete that slice. Let's delete the layer, and then let's add a region. So when adding a region, same deal as the slice, same behavior as a single data set. Specify the field type, field name, left, right edge, resolution you want to slice at. So this resolution you want to sample at. This resolution, though, when you're sampling a whole time series, is pretty important. So this is all happening in memory, which means that you have to be able to fit all of these arrays in memory. And that can be a challenge depending on how finely you sample. So for now, let's actually keep the high resolution, but really decrease how frequently we sample. So let's go from 1 to 46, 47 at, let's sample every 10th. Okay, so what you get out is, since we still have the load as stack checked, what you get out is actually a 4-dimensional array. So when you look at it in Napari in 2D, you get 2 sliders. The first one slides through space, and then the second one slides through time. And if you look at it in 3D, you get out the current time step in 3D. And you can use the slider to step through time now. One kind of fun thing that I don't think I've touched on in earlier videos is, so these, one of the options up in our layer controls here, this depiction option, set to volume right now. So if you change that to plane, it takes a planar slice through your data, and if you shift click on that plane, you can actually drag that plane up and down through your data set, so you can kind of find an interesting spot and then step through time and look at how the, in this case, density field evolves along that plane. So that's just kind of a cool aside that I don't think I've mentioned yet. And then let's switch that back to volume. Yeah, so you know, similar to a single data set, you can add multiple regions, either vary the region or add a same region, different field. And that is about, that about covers the how you work with this from a GUI. From a notebook, you actually have a lot more control, and so we'll talk about that. You can do all the same things, but some extra, along with some extra features, including, we'll get to this in the next video, but we'll talk about how to use Dask in order to sample every time step at a higher resolution region without overwhelming the memory. So that is something you can only do from the notebook. So let's actually go get started using the notebook interface. Let's close our Napari viewer and start up our notebook. Okay, let's import what we're going to need. So we want Napari, we want to import yt-napari, and actually we'll do from yt-napari import Timeseries. And let's start up a Napari viewer, just to have that ready to go. And let's take a look at this Timeseries module. So there's a number of things here that are relevant. So the main thing is this add to viewer function. So what this does, similar to the loading a single data set in, you provide it the Napari viewer, and you provide it selection, and additionally you've provided all of the file matching parameters that we looked at in the GUI. There is also the load a stack option, similar to the GUI, and then some others that are not available in the GUI that we'll talk more about later. But in general, the way this works with time steps is, unlike yt proper, so in yt proper, let's say you have a data set. So if you do a yt.load sample Enzo Tiny Cosmology, this will fetch and load just the final time step from the Tiny Cosmology series. So in in YT, normally the way you would create a selection object is by using the attributes that hang off of the data set that you're working with. And so that data object gets associated with a particular data set you have. In yt-napari, these data selection objects are standalone objects that get applied to each time step. So there's right now there's a region object for a 3D region, and then there's a slice object for a 2D slice. So both of these take a field and then arguments for the bounds and the resolution you want to sample at, and then you hand that off to the add to viewer function, and it'll go and apply that selection to each of the time steps. So let's actually do that with the slice first. So slice timeseries.slice. So you give it a field as a standard YT field tuple, cast density. Give it a normal. If you don't specify anything else, it'll just take the full bounds available for each time step. Resolution, we keep that. And then to actually use it, use our add to viewer function. We give it our Napari viewer, we give it our slice object, and then we give it our parameters for matching files. So in this case, I'm going to actually put the directory within the file pattern itself. And then let's load as stack. And then let's give it a color map. So unlike in the GUI, you can pass along any keyword arguments that the Napari add to viewer function takes. So you can set color maps, you can set contrast limits to use initially, you can set give it a name. So let's give it a name. Let's call this slice stack density. And let's see if there's any other things I wanted to set here. So this final argument here, so you remember when we looked at the 2D slice stack in 3D, the third axis is the time axis, and in the GUI that just gets tacked on to the end so that each layer is separated by a single pixel. But from the notebook, you can provide this stack scaling argument to spread out that time dependence. And that makes looking at it in 3D a little bit more interesting. Okay, so let's do that. And I forgot that. So if you just go and do that, you'll get all the output as it goes and loads every time step, or every time step. If, however, up here I had done set log level 50, we would not have gotten all of that. So if you want to avoid all this output, set your log level to 50, and you will only get error messages. Okay, so it's going to load every time step. That'll take a little bit more time. Let's go over, and I think we're almost done. Okay, so now we have our stack. So as before, you slide through time, and now because we've provided that scaling argument, you can actually look at the time history in that third dimension. And one of the other things that working from a notebook gives you is a bit finer control over where you want to center slices. So for example, let's say we want to load up our final time step. And let's center a slice around the location of the final maximum density. So first let's find our what that location is. So we'll look at all data quantities dot max location, and we'll look for gas density. And what you get out is the value of the density as well as the position. So let's create our new center location based on that. And we'll put that in an array. And let's set a width of 15 megaparsecs. And let's create a new slice. So we want our gas density center is equal to center, width is equal to width, height is equal to the same value. So we'll use this 15 megaparsecs for both width and height. And we also need our normal. So let's go normal to X and keep the standard resolution. So let's do that, and then we'll go back all the way up because of all that output. Actually, let's run that and see if it takes effect. So let's add our new sample. And run that. So you'll see that we get much less output here. Just the info on the grid hierarchy as it gets built for each time step. And now, as we look through time, we see that our final location is centered on that maximum density value. And you can see how leading up to it, there's these two high density regions that merge together. And now when we look in 3D, you can actually see that history of that merge spatially. So this time axis distance is arbitrary, but it does kind of spread things out for you nicely to see how that changes. Cool. So quick side note about this, the way that this slice object works. So when you initially create this slice object like this, it'll right away take the center and find the bounds by subtracting off the half width and adding the half width. So what you get out is a left and right edge essentially that are in your code length coordinates. And so what you get out when that is applied to each slice is oops, it's gone now, but you get a slice that is visually the same size throughout time. You can, however, also specify these center and width and height arguments as tuples, so that, for example, we could say instead our new center is going to be our center under values. So this will just be the numpy array from the unit array, and we'll give it the code length units. And then our width, we're going to take 15 megaparsecs. And now when we build our slice object with these new values, this will actually be applied to each slice individually, so it won't calculate the extent of your slice until each time step is loaded, which means that we'll still be following our center coordinate in co-moving coordinates, but for each time step it'll apply this, it'll calculate a distance, a physical distance that will actually vary over the length of the simulation. I'm not actually an astrophysicist myself, so I found this very confusing initially, but if you are like me and not super familiar with cosmology simulations, just remember that the universe is expanding, and so these simulations are effectively done on a normalized length scale, and so by providing a center and a width as a tuple, you actually get the slice extent set by the physical distance, the absolute physical distance for each time step. So if we do this and load it back in, and wait another 20 or 30 seconds. You will get out a slice where the bounds actually change in time. So initially 15 megaparsecs is much wider than the physical distance of the domain, and so as you go on, eventually the physical domain grows to be much wider than 15 megaparsecs, and you get a fixed window into that, and if you look at it in 3D, you can see how that changes in time. Great, so the one quick final note, won't go into this too much, but just like the slice object, you can have a region object. So this one, you provided a field, a left and right edge resolution, and then just with the slice, you give it to the add to viewer function, and it'll go to all of the time steps that get matched and sample that region in 3D. With, as I mentioned in the GUI, though, you can have problems with memory here. So if you actually go and load in every time step at a pretty high resolution, you can easily exceed your available memory, especially if you load it as a stack, just because you'll end up with needing some extra memory to concatenate all of those. But you can get around that using Dask, and I'm going to talk about that in the next video, and so I'm going to not talk about using the region object from the notebook quite yet. And yeah, so that covers everything I wanted to talk about in this video. So as I said, next video we'll continue on the time series topic, but bring Dask in to speed up some of this processing and load in regions in a more efficient way. So see you in the next video.